Hey, it's a pleasure to introduce the third speaker of the night who will speak about transverse string topology and not, and it's Michael Sullivan.
All right. Well, if I told my Dennis stories, we would definitely miss the bus. So I'll just jump right in. Okay. Transverse string topology and knots. So this is joint with Dennis. Okay, so time permitting, I'll also talk a little bit about transverse closed strings and some other modifications you could do to apply this to transverse knots and Legendrian knots in contact free manifolds, but probably the time won't permit that. Okay, so I don't know if there's not much of a, there seemed to be an audience shift between yesterday and today, but in yesterday's talk, Abu Zaid briefly mentioned something, a result of Lenny-Eng, and so that's the motivation of this talk. So basically, what he was referring to is known as the Eng chord algebra, and it works as follows. Supposing I have a knot, which is an embedded circle in R3 or S3. Eng defines an algebra where it's it's called chords are going to be the same as chords in that board over there. It's the tensor algebra with unit, freely generated by chords up to chord homotopy. Oh, let's see, when did I start, just so I could pace myself? Okay. Over the group ring Z with this formal variable mu plus or minus 1 adjoined, mod certain relations, relations 1 and 2, which I'll describe with pictures. So color. All right, so relation 1 is if red denotes my knot K and white is the chord, and I have a little short chord like this, I'm going to set it equal to 1 plus mu, an element in the ground field, ground ring. And the second relation, okay, so here I have a string passing under and a string passing over, and that's going to be equal to, oops, that's going to be a quadratic term in this tensor algebra given by that. You've seen Somnath's talk, and really what you're supposed to think of this as kind of the resolve operator in this knot case. And this kind of really is the motivation for this, a lot of this. Although his is really the tensor algebra. It's not this square algebra. Okay, so that's roughly the invariant. There's another version, slightly more refined, with an extra parameter floating around, but I won't mention it. So then there's this theorem by Lenny-Eng. Actually, this is like a number of results, just demonstrating the usefulness of this, and that's certainly not a homotopy invariant. I can say a lot about the knot. So first of all, this tensor algebra, well, it's not tensor algebra anymore, but this algebra recovers the Alexander polynomial of the knot. If you set mu equals to 1, it detects all knots with less than or equal to 11 crossings, distinguishes. And that's just because that's how much the computer could do, obviously. Something special about 12, as far as I know. And it's possibly a complete invariant. That is, maybe it could detect any 2 knots. And then, yeah, I'll skip this one. Another one is that, obviously, I mean, if it's computable, and in fact, more specifically, it's quasi-isomorphic. Well, here I think of this as having a zero differential when I say that. It's quasi-isomorphic to the degree 0 part of some graded differential graded algebra, which I'll call combinatorial Ang, because he also defined this one. And this is the one using some sort of braid relation of a knot that you can plug into a computer and compute program. OK. And then, the theorem that I want to talk about that's joint with Dennis is just that this open transverse string topology determines Lenny's chord algebra. And there's one more result, and this is kind of links into the first talk of this evening. And in a somewhat more significant way, the first speaker, Chen, mentioned how his talk was inspired by Yanko Leitchev and Kai Chilibek's relation between contact homology and string topology. And so this is kind of the same motivation because, in fact, there's a theorem, theorem by Ekholm, Etnayer, Ang, and myself, that this combinatorial differential graded algebra for a knot, let's say K, is quasi-isomorphic. So I'm not going to describe exactly what this is, but it's some sort of Gromov-Witten theory, which means count, well, in our case, holomorphic disks associated to. So I'm just throwing these words down for people who know this. I'm not going to talk about this very much at all, or in fact, any at all, other than the statement. The Lagrangian cone of K in the symplectic manifold. What you do is you take S3 and you take, well, let's say, to use Chen's notation, you would take the disk bundle. This is the unit, and then you take the boundary of that. So that's a contact manifold. I forgot actually what he called this, but I'll just call it this. So this is the unit cotangent bundle. And then you cross it with R, so you take the symplectization. So that was this non-compact symplectic manifold. Okay. Yeah. Okay. So so this kind of gives a kind of a relative version of the first. Well, a relative version. I mean, a relative related version of the first theorem from this evening, that you have a kind of string topology construction and a holomorphic curve construction. Okay. Oh yeah, for those who know, this particular Gromov-Witten theory is the Legendrian contact algebra. Okay. Oh no, this is what I want. Right. Okay. All right, so just a few comments. So, like I said already, if you look at this relation, but you plug in mu equals -1, it looks like the coproduct. And so, bad Blackboard management. I need this board here. Okay, I'll start over here. Can you get that with the camera? Maybe. Okay. Are you getting that with the camera? I should say more. Anyway, so So relation 2 looks like a traditional coproduct with mu equals -1. However, it's not clear how interesting this invariant is with mu equals -1, but unclear what the invariant computes. It's definitely interesting with mu equals +1, but mu equals -1, that's open. And then the second point is that even if you were to do the coproduct, there's a traditional problem that if there were some alleged coproduct, and you wanted to look at, you want to define it and you want to extend it to chains, let's say traditional, there's some sort of, as Dennis calls it, an anomaly. And so, right. OK. So this is kind of taken care of. Yeah.
Move things and make them transversal?
Yeah.
Okay.
Yes. OK, so, right. OK, so now I'll go back here. So I should mention, so it's a little weird to put mu equals +1 if you haven't seen Somnath's talk. So McGavin had an idea of just, well, let's just take it for what it is. And what he does is he kind of generalizes Eng's chord algebra to higher degrees. And it's still perhaps an open question if this chord algebra does in fact equal the combinatorial version, which I didn't define, but just said it was combinatorial. But the combinatorial one is the one that's kind of interesting because it comes from Gromov-Witten theory. So it's possibly equal to and then, you know, as you saw in the last talk, Somnath then kind of takes this idea several steps further and actually sets up this formal framework at the chain level and expresses it as a cobar construction. And I don't know if he mentioned this, but his examples are lens spaces that he then goes on to apply and show that it's useful. So, all right. My one piece of color. OK. So I'm going to, let's see. This takes so long to give me time. OK, 11 minutes. So rather than restate that, I'm going to recycle this board and just maybe tweak the notation a bit. So hopefully you remember this picture, and it's good that he actually did it for the knots. We have these strings, and we take a chain complexes in cobar, and we recover chain complexes of the chord. And if you complete this picture and you have the fibration involved, the fiber in this particular case is going to be chains on the base loop space of the complement. So now for us, instead of using X as a product space and Y as a diagonal, we're going to use X as S3 and Y as the knot. So let's apply Somnath. Equals a knot. And so we recover, in this case, we get from open string topology, transversal string topology, we get this fiber, which I'm going to, since I use different notation, I'll just use my notation. We get a model for the fiber, which in this case is going to be, so you can think of it as the fundamental group of the knot complement group ring generated by that. But there's a little thing here, twisted. So it's not just usual concatenation. It's in fact going to be this. All right, so this is what doesn't get erased, right? That's not bad. Twisted. That is. So I think did he use a notation star? No. Maybe it was. Maybe I erased it. Okay. That is, if I take two elements x and y in this group ring, the twisting can be expressed for this special case as he was drawing. Xey plus xmy, where we have so here's the knot. Here's x and here's y. Two transversal strings, two transversal chords, in fact, because we're in the group ring of the complement. And I'm using E because it's kind of like you can think, it does not as drawn this way, but you can think about it if you match this point with this point, that E is the identity element in the fundamental group of the complement, and M is the meridian. But maybe it might be better to look at it and draw it that way. And so just to note that this group ring doesn't, untwisted it has obviously a unit, namely the identity, but twisted it doesn't. So for example, even if you take the unknot and you look at the twisted group ring, so this is one generator. But if you look at this twisted structure here, it's not even close to being E is not even close to being the identity. So you get, I guess you just get this. It turns out you can just play around with this, and you can check that this group ring is generated by the constant loop and the meridian in the opposite direction with some funky relation here. Well, not so funky, actually, it's useful. Anyway, that's just from a couple drawings. Okay, so finally, we can kind of get to the application. All right, so we have we've recovered. So from open string topology, we have this guy, and we want to get Lenny's chord algebra, and we're going to do it as follows. So given a knot in S3, let's let L denote the corresponding long knot in R3. So this is going to take me 5 minutes to figure out these crossings. So I'm just going to guess. This one, that one, this one? I don't know. Anyway, so this is some knot in S3, and I remove this little ball here, and I get this long knot in R3. We think of isotopy classes of regular knots. Here we look equivalents of long knots as isotopy classes with compactly supported isotopies. Okay, and we're going to look at a little tube here, like Somnath was looking at, and we can look at. So let's let R be the twisted group ring. So I should mention. Really, actually, we want to apply this to R3 and a long knot as well. So let's let R be the twisted group ring of the complement of this long knot. Now I'm going to add a unit formally. Okay, there doesn't exist a unit naturally, so I'm going to add it. And I can look at some subring be the twisted group ring of the tube, complement of this long knot in this tube, and add a unit. Okay. Right. Okay. And then I'm going to define, I'll denote it ST because it comes from string topology, would be the constructions we've done. I'll take this ring and I'll make the subring commute with everything. And then finally, we get to the result that this thing is now Lenny's chord algebra. So Lenny's chord algebra for the original knot in S3 is going to be this guy. And this is actually as an isomorphism, because there's no differential here. We've already kind of passed to homology. We went to the group ring. These are as algebras. You can view these. Ang, right, that looks like an axiom. Let's see, ang on the left. Thank you. Right. Okay. So I got a couple more minutes, right? Okay. Now I can erase this. So that's another application after the lens space application, because we already know that this is not a homotopy invariant. Okay, so so I was hoping these would be results by today, but now they're still just questions. So we can generalize this. So in addition to having these strings be transverse at the knot, we can also ask that they be transverse at any, if you have, for example, 2 copies of a string, you can ask that the pair be transverse if they're transverse at every point of intersection. So just recall what you can do with so with a knot, we had, Somnath describe these 2 operations where you can split. This is actually just 1 string already. Or you can resolve. Okay. You can also do this at the if you assume transversality at interior points. You can do this. You can replace the knot with another string and do the same operation. So now I have like 2 strings, for example, and I can do this. I should have done it this way, just to make sure. I'm sloughing over some stuff because we have to have an ordering and so on to be able to do this. And so this kind of local operation leads to, and you can, let's say, closed or open strings. So this sort of local operation leads to the product or the coproduct or the bracket or the cobracket, and this one unnamed. And so one thing you might hope for is another kind of knot invariant. So I'll leave it as a question. Can these transverse operations recover the bracket in the knot complement So remember, although these strings are transverse to the knot, they are going through the knot. So but can you do some construction like, well, it would be more complicated than what we did in this fiber, but to recover information about the knot complement, the bracket and the knot complement, because then, if you could, then you would use the talk from the first day of this conference. And you would be able to detect, well, say something about the hyperbolic ciphered decomposition of the complement in this case, using Moyerchef and Siddhartha Gadgil. Most of you probably weren't at the first talk, but including myself, unfortunately, because I heard it was a great talk. You can do this. Use just the bracket on the first and zeroth homology and say something about what that three-manifold looks like in terms of that decomposition. Let me just say in words, since I'm out of time, just some other manipulations you could do. So now supposing the contact manifold, the three-manifold, instead of being S3, was just some contact manifold, and supposing your knot was a transversal knot or a Legendrian knot. And what that means is that it's basically contact manifolds. For those who don't know, just think about a two-dimensional distribution in this three-manifold with some properties. And for transversal Legendrian knots, just think of knots that are either always transversal or always tangent to this distribution. That's basically the definition. And you can see that you can kind of further restrict strings this way. Say, well, keeping the property that they're going to be transverse to the knot at its ends, that will translate into conditions about what the strings look like with respect to this two-dimensional plane field. And so you immediately get Legendrian knot invariance and transversal knot invariance this way. These Legendrian and transversal knot invariants are also kind of Gromov-Witten type invariants. They come from holomorphic curves. And so you can just say, well, is this string topology for this theory going to give me these Gromov-Witten curves for that theory? Anyway, so this leaves 35 minutes for Scott and people to get to the bus, so I think I'm going to stop here.